Greetings and welcome, everybody, to the 2021 McDonnell Distinguished Lecture. I'm Brad Jolliffe, Director of the McDonnell Center for the Space Sciences, and it's my pleasure to welcome all of you this afternoon. We have fellows of the McDonnell Center, members from the Departments of Physics and Earth and Planetary Sciences, affiliated members and colleagues, alumni, Dean of Arts and Sciences, Feng Sheng Hu, and very special guest, Mr. John McDonnell. Indeed, at Washington University, we're very fortunate to have the McDonnell Center for the Space Sciences, which is made possible by a very generous gift from the McDonnell Foundation and later supplemented by the Danforth Foundation. So every year in the spring semester, the McDonnell Center hosts a distinguished scientist to give a lecture on an issue of great interest and importance in space science. And today, we're honored to have Professor Katherine Freese, the Jeff and Gail Kodosky Endowed Chair in Physics, University of Texas at Austin, delivering the distinguished lecture on dark matter in the universe. Ordinarily, she would be here in person, but she graciously agreed to do this remotely. And given the circumstances, we're especially appreciative. I'll reiterate the offer that I made to her beforehand that in the future, she's always welcome to come for a visit and the center will pick up the tab. Now I'd like to ask Professor Mark Alford, Chair of the Department of Physics, to introduce our distinguished lecturer. Mark?
Yeah, can you hear me okay?
Yes, we can.
Okay then. Okay, well, it's a very great pleasure to introduce Professor Freese, who I've known for a number of years and is an extremely prominent figure in cosmology, in our understanding of the universe, and has even written a book on the universe. And my belief is that when people write books about the universe, they're basically telling you something about themselves. Well, hers is called The Cosmic Cocktail, 3 Parts Dark Matter. So I think that tells you something about the spirit of kind of fun and wit with which Katherine approaches this subject. Her book is very approachable, and I can recommend it for anybody who's interested in delving further into these things. Really, you can see already from the qualifications that are on your screen here, she's been the director of Nordito, one of the world's famous institutes for theoretical physics. She's now at UT Austin. We're very lucky to have her here to tell us about dark matter in the universe.
Well, Mark and Brad, thank you so much for the kind introduction. I'm so happy to be doing this. And yes, I absolutely want to come visit in person as soon as that's possible. So before I delve into my subject, I always like to think about humanity, about people in antiquity. They must have been very similar to us, asking similar questions. Where do we come from? Where are we going? What is out there in the universe? And so throughout the ages, people have had creation myths. And starting 100 years ago with the work of Albert Einstein in 1915, we have our own creation story, the hot Big Bang. But the thing that's so remarkable is that we actually got it right. So the amount that we've learned about the universe in the past 100 years is just breathtaking. So the Big Bang isn't a complete story, but it is basically correct. And that's just phenomenal progress in human history. So now I have to figure out how to move to the next slide. Here we go. So in addition to the enormous progress over the last century, since the turn of the millennium, there has been really an acceleration even, not only of the universe, but also of what we've learned. So some of the big questions have now been answered. We know the geometry of the universe. We know the energy density of the universe, the age of the universe. We understand the basic physics all the way out to the edge of the observable universe, because the observable universe is defined by, well, if it takes light, if it travels at mostly the speed of light, the maximum speed is set by the speed of light, then the farthest out we could ever hope to see is the age of the universe times the speed of light. So we understand all that basic physics, and yet we don't know what the universe is made of. What is the dark matter? What is the dark energy? So as far as some of the progress that has been so amazing in the past several decades, the leftover light from the Big Bang, the cosmic microwave background, has been one of the probes that has offered us answers to some of these very deep questions about the universe. So this is data from this Planck Space Telescope, and these red spots and blue spots are regions that are slightly hotter and colder than the average place in the universe. And it's from the size of these hot and cold spots that we learn what the geometry of the universe is. If the geometry of the universe is flat, in other words, it has no curvature, then light would be moving in straight lines, and we should see the angular size of these hot spots to be 1 degree in scale. And that is exactly what we see. So here is the 1 degree in angular scale, and that is exactly where there's a peak. So this is known as the Doppler peak, and it tells us that the geometry of the universe is flat. Now, from Einstein's relativity, we know how to connect geometry to mass and energy content. And so this geometry means that the total energy and mass of the universe is about 10 to the minus 29 grams per cubic centimeter. And that is in contrast to Earth, where the density of water is 1 gram per cubic centimeter. So this is very diffuse. I tried once to explain this to the Queen of Sweden, and it was a bit of a fiasco. Feel free to ask me someday. So from this Planck data of the cosmic microwave background, not only do we learn the total content of the universe, but we also learn about a lot of other things in cosmology, including the 6 basic parameters that are fit to those 7 peaks in the data. And among other things, we learn about the, I'll tell you in a second what we learn about it, but I want to tell you this joke first. So this is earlier data from the WMAP satellite, the NASA satellite, and here we have the initials of Stephen Hawking, and they're still there in the Planck data as well. But what we learned from these experiments is the breakdown of the universe is very peculiar. So the ordinary stuff that we're made of, the atomic material, is only 5%, whereas dark matter is 25% and dark energy is 70%. And so it is our job to try to figure out what this dark side of the universe is. I also like to point out that the NASA satellite has slightly different numbers than the later Planck satellite. So Planck is for some reason giving us slightly more dark matter than WMAP did. Of course, it's the same data. We only have one universe, so someday this discrepancy has to be understood. But in any case, the 70% dark energy and roughly 25% dark matter is something that we want to understand. Now, this dark matter problem is actually quite old. It dates back 90 years at this point to the 1930s. When I was in Sweden, I learned about the work of Knut Lundmark, who actually figured this out even earlier than Fritz Zwicky. Here's a picture of Zwicky, who famously studied the galaxies in the Coma cluster, and he realized that the ones on the outskirts were moving too rapidly. In other words, based on the stellar material that he could see, you can figure out from the gravitational pull how fast things should be moving, and they were moving too rapidly. So there must be something else speeding them up. And he proposed dunkle Materie, the German for dark matter, as the explanation. And the word dark here is very simple. It just means it's not stars, it doesn't shine, it's dark. So Zwicky was a character. You may have heard the story that in his book, he wrote that his colleagues are spherical bastards because they're bastards no matter what direction you look at them from. So not sure I would have wanted to be his graduate student. So subsequent to the 1930s, where there were these first suggestions for the existence of dark matter, there were a lot of other people doing studies, but it was really the work of Vera Rubin and Kent Ford in the 1970s that nailed it. And that's because they looked at galaxies and found that all of them contain dark matter. So this problem is ubiquitous, and the scientific consensus became that we really do have to go understand what it is. So in these original studies, what they did was look, if this is the center of a galaxy, they looked at stars and gas moving around the center. And of course, the speed of this motion, of this orbital motion, is determined by the mass interior to that radius. And so here we have essentially the virial theorem. And again, the velocity is determined by the mass interior to radius r. So more mass means faster orbits, and they found really fast orbits compared to what there should be based on simply stellar material. So if we look from the center of a galaxy, moving out at various radii away from the center, how fast things are moving, then based on the stellar light alone, the velocities should drop off as you move it farther out. But that's not what they saw. Instead, they saw these flat rotation curves, and the way to explain that would be to have additional material in what we call the halo of a galaxy. So if you add that in, then these rotation curves make sense. Let me show you a picture of our galaxy, the Milky Way. At the center, there's a supermassive black hole, and this is really fun because it was the origin for half of the Nobel Prize in 2020 in physics for the discovery of this supermassive black hole at the center of our galaxy to Andrea Ghez and Reinhard Genzel. And that black hole weighs 4 million times as much as the sun. So moving out from that black hole, which is shown in yellow just so you can see it in this diagram, then as you move out along this pinwheel of structure, you have the spiral arms where the stars are located in the Milky Way. So here's the sun, for example, along one of these spiral arms. Then if you take all of this and you put it on its side, then this is what we call the disk of the galaxy. So there's this flattened central region with the sun, again, 25,000 light years or 8 kiloparsecs away from the center. And all of that is only a tiny, tiny piece of the total. And so if you look at an artist's impression, then here's the spiral structure, but there's this giant spherical region out here that we call the halo of the galaxy, made almost entirely of dark matter. After the initial discovery that dark matter should be there from the point of view of rotation curves, it at this point has become a jigsaw puzzle with many, many, many pieces, all telling you the same thing. There has to be dark matter out there. Another way to look for it, again, dates back to the work of Albert Einstein. This is lensing. So if you have mass of any kind, and it could be dark matter, it could be a massive compact halo object, it doesn't matter. So the dark matter doesn't give off light, but what it does is bend the light that comes from behind it. So a star gets bent as it passes by the mass on the way to our telescopes, so that we might think the star is in the wrong place, but then we would notice, well, we have multiple images of that same star and the star is distorted. So by looking at the background light and how it is distorted by the mass in between the stars and you can figure out how much dark matter there is. In fact, there's an app on your phone that was written by Eli Reichoff, a Michigan graduate student, that has the correct equations of gravitational lensing if you'd like to lens yourself, which these students did. They lens themselves more and more. So then I do want to show some real data from Hubble Space Telescope of lensing of distant background galaxies and look at these sheared objects and multiple images. And this is quite a complex structure, a lot of imaging of lensing going on. And based on what happened to the background stellar light, you can, with a computer, reconstruct the dark matter in between that light and you. And if you do that, you get an image like this. But I want to be very careful because this image is not from the same one as the one in the previous slide, but it's also a computer reconstruction of different Hubble Space Telescope data. It's just the most stunning picture, so I like to show it. And so here you have multiple galaxies. That's what these peaks are. This is the density distribution. And then underneath the galaxies, again, you have a lot of dark matter. So the clusters have even more dark matter in between the galaxies. Then there's a famous piece of evidence in favor of the existence of dark matter. This is called the bullet cluster. And this was on the slide that was part of the advertisement for my talk. So what we have going on here is that there's two clusters that have collided with one another. And so when the two clusters did that, the gas got stuck in the collision. So for example, if you and I collided, we would get stuck. We have electromagnetic interactions, we have strong interactions. So that's what happens with the ordinary matter. And that's shown in pink as because it's detected in terms of X-ray emission. However, there's a clear differentiation from a different type of mass, the stuff in blue, which was detected by lensing. And so this dark matter did not get stuck. Instead, it kept going. So it interacts far more weakly. It doesn't have stronger electromagnetic interactions, and it just kept going on this first collision of these two clusters. So to reiterate, we know from many, many pieces of evidence that dark matter exists, and most of the mass in galaxies is dark matter. And we know this from rotation curves, gravitational lensing, the bullet cluster. The most important in a way that it's the thing that you really can't argue with is the peaks in the cosmic microwave background that I showed at the very beginning. There's also evidence already from the 1980s from Big Bang nucleosynthesis that I haven't had a chance to talk about. It is fun also to show that a series of slides here which show that without dark matter we could not exist. So ordinary matter doesn't clump rapidly enough because it's tied to photons, and photons stream out of things. So if you want to make galaxies, you need the dark matter to do it, and then the ordinary matter falls in later. So in this slide, this is very early in the universe. This is showing the dark matter particles in blue, and so this is a numerical simulation which contains only dark matter in it, and it's going to show how the dark matter that's initially almost uniformly spread out, but not quite because of inflationary initial conditions. So you have these slight inhomogeneities, and the dark matter is going to clump together to make more and more structures of different sizes. So as time goes on, this is how the universe evolves until you get to today, where you have these long filaments of structure, and the galaxies are at the nodes of these intersections of the filaments. So I've argued for how we know about the existence of dark matter. And well, of course, that doesn't tell us what it's made of. So we have to, that's the big question that is the motivation for my talk today. So initially people tried the obvious things like gas or lumps or snowballs of hydrogen or rocks, and all of those would have had observational consequences that ruled them out right away. Then there were still two camps, and this is before we knew what the total energy density of the universe. There were people who thought, well, it could still be massive compact halo objects, machos. And the reason that this would make sense is because although it wasn't bright stars, what if it was faint stars or even substellar objects, because things lighter than 0.1 solar mass don't light up, they can't get fusion going. Or what if it's stellar remnants, white dwarfs, and so on. And so these are the massive, the macho possibilities, which would be made of ordinary matter. And then even in the 1980s, there were people already saying, no, we need something that's non-baryonic. It's got to be something more exotic, WIMPs, axions, or whatever. So we had the machos versus the WIMPs. I participated on both sides of this debate, and it is quite clear that machos don't do it. So we showed from a combination of theory and observations that this faint stars or substellar objects can only be they make up like 3% of the galaxy, and the microlensing experiments carried this all the way down to even Earth mass objects. Stellar remnants is still possible. There's a significant component of white dwarfs, but certainly baryonic dark matter is not enough. That takes us to exotica. Now, well, there was one possibility that's not exotic, and that was that, well, what if it was neutrinos? That's so great because neutrinos do exist. However, it was clear right away that wasn't going to work for several reasons. Well, neutrinos are too light. So first of all, it was clear that they would ruin galaxy formation because again, since they're very light, they stream out of things. They don't create structures, they would ruin them. And in fact, although, so as far as the dark matter story, this is actually originally work of Kausick-McClelland, and the contribution of neutrinos, and this is the normal neutrinos, the active neutrinos, to the energy density of the universe depends on their mass. And so it turns out if you had neutrinos that weighed 50 eV, that would give you the entire universe. This is the fraction of the universe, omega neutrino, and the entire universe would be made of neutrinos, in fact. But instead, what we now know is that the sum of neutrino masses adds up to roughly 0.1 eV, which means neutrinos contribute only 0.5% of the mass of the universe, which certainly is not enough to explain the dark matter. Well, what do we know about neutrino mass? It's not dark matter, but because I've been working in this area and there's a lot of activity in cosmology on understanding neutrino mass, I wanted to delve into this subject a little bit in my talk. So the Nobel Prize in 2015 went to the measurements of neutrino oscillations, which give us mass differences. So we know that the difference between nu1 and nu2 from solar physics is given roughly by 10 to the minus 5 eV squared. This is the difference, the mass difference squared. And the nu1 is made mostly of nu e. But the mass eigenstates and weak eigenstates are not exactly the same. So 1, 2, and 3 are the mass eigenstates. And over here, nu3 is made mostly of nu tau. And we know the mass difference from atmospheric neutrinos, and that's at about 10 to the minus 3 eV squared. But the funny thing is, we don't know, are nu1 and 2 the lightest, or is nu3 the lightest? So it could go in either order. And depending on that, it's normal hierarchy versus inverted hierarchy. What we do know from adding these numbers together is the sum of neutrino masses has to be bigger than 0.06 eV in any case. But what we learn from this is neutrino does have mass, which means it is the only known piece of physics beyond the standard model of particle physics. So that is a big deal, and we need to understand it. However, from these experiments, all we have is the relative mass differences between the species, and we need to know the absolute scale of neutrino masses, and there are many ways of going after that. I wanted to mention neutrinoless double beta decay because it allows me to put up this slide, the latest limits on neutrinoless double beta decay, and some of you will recognize this young man, Douglas Adams, the first author on this paper, so I had to show that. But what I really want to get to is what cosmology can do for neutrino mass. And it's really remarkable how well it does. Actually, my very first paper ever was bounds on neutrino properties from cosmology. But at this point, it's just remarkable because if you combine in this plot the information from the cosmic microwave background together with large scale structure, then that limits you in this plot. And I should tell you what the axes are. The sum of the neutrino masses of all 3 neutrinos versus the Hubble constant. What we found was the sum of neutrino masses has to be less than 0.15 eV. And isn't it fun? We actually got our work published in the Particle Data Group's review of particle properties. Since then, the bounds have improved somewhat. It's 0.12 EV. So let me remind you, from oscillations, we know it's greater than 0.06. So we're really, really, really narrowing. Cosmology is playing a huge role in narrowing down what the value actually is for the neutrino mass. I also wanted to say that everything I've showed you from cosmology. Oh, yes, I wanted to show you what neutrino mass does. Well, neutrinos ruin small scale structure. Okay, so the more massive they are, the power on small scale structure goes down. So that's what they do. That's how we can find bounds on how many there are. And I also wanted to say that what I've shown you so far is for the standard lambda CDM cosmology, which makes assumptions about the dark energy. But it turns out as long as you have an equation of state always greater than or equal to -1 for all times in the past, then the bounds actually are stronger. The bounds on neutrino mass get stronger if you have something that's not a cosmological constant, but it has time variation or whatever. So that these bounds are really solid. So I also wanted to tell you about something that I've gotten involved in, which is the cosmic microwave background experiments. And I've joined 2 of them, the Spider at the South Pole and the Simons Observatory. And originally my motivation was because I am interested in inflation, and I have a model called natural inflation. I want to know what is R. But what I hadn't appreciated is how well these experiments are going to do on the sum of neutrino masses. This is huge sensitivity that will come out of the Simons Observatory, which is located in Chile in the Atacama Desert. So scaling it up here at 17,000 feet above sea level. And yeah, it's going to start taking data in a couple of years. It's exciting. So where are we with neutrino mass? Well, it's close to being measured. We know that we have a lower limit from oscillations, and then we have these upper limits from cosmology. So we're really nailing down what neutrino mass is. Now, there is a possibility of that the dark matter is made of sterile neutrinos, which would be a 4th species that doesn't have standard model interactions, but it would mix with ordinary neutrinos. And I just wanted to mention some of the work of the young people in my group. So this is Stefan Hagstutz and Pablo Fernandez de Salas, and this is just a very light neutrinos that weigh less than a keV, combining all the bounds from cosmology and laboratory searches, and seeing what light sterile neutrino mass there could be. So let's return to this question of what is the dark matter, and there are many, many possibilities that people are playing around with. And so I've mentioned the neutrinos. There's also primordial black holes. Florian Kuhnel was in my group, and he is one of the people working on that. I know that Francesca Ferrer also is. And the reason that they've become popular lately is because of the question, did LIGO detect dark matter? So LIGO, as you know, has found black hole binary mergers, but it is possible that those could be primordial black holes. So people are paying a lot of attention to that. While we're on this subject, this has nothing to do really with my talk, but I have to tell you because I'm excited about it. So it turns out that LIGO has also found bizarre, to everybody's surprise, black holes of masses 66 and 85 solar masses, which should not exist in standard stellar evolution because their precursors would have exploded as pair instability supernovae. So what we did was say, well, what if there's an additional source of energy inside those precursors, for example, due to dark matter or whatever? We're agnostic as to what it is. And then you can actually end up making these black holes that are seen in LIGO. So that was fun. So let's get back to the question of what is dark matter. And I'd like to actually go back to my slide here because there are two WIMPs and axions that have the best theoretical motivation. And so I wanted to tell you, mention something about that. And so the reason I say they have the best theoretical motivation is because neither one was invented purely for the reason of explaining dark matter, but instead they have other reasons to exist in particle theory. So I will say very little about axions, except they're very light and yet non-relativistic. And they are an automatic consequence of a solution to a problem in QCD, the strong CP problem in QCD. So they automatically would exist. And again, wanted to mention a person formerly in my group, Luca Visinelli, who wrote a nice review about the experimental situation. And so here we have the axion mass versus axion coupling to photons. And from the QCD axion, to solve this problem that I mentioned, you should be in these yellow bands. And beyond that, people are interested not just in the QCD axion, but in other axions that come out of string theory, and they could have a wide variety of possible masses and couplings, not as strongly motivated as the QCD axion. And in particular, the ADMX experiment is about to probe a very interesting regime in parameter space. I know that James Buckley is part of that. So I'm going to turn to the subject I've spent a lot of time working on, and among the best candidates for dark matter are the WIMPs, which stands for weakly interacting massive particles. So these guys, there would be billions passing through your body every second. I know this because a reporter asked me, so I had to figure it out. And about one a day to one a month hits one of your nuclei, but doesn't do anything because, as I said before, it's not likely to have strong or electromagnetic interactions. Well, of the four fundamental forces, there's one left, and that's weak interactions. So that's what these WIMPs have, or they do feel the weak force, and they weigh about 1 to 10,000 GeV. So there's two reasons why WIMPs are popular, and one of them is that if you have only one ingredient, the weak interactions, then you automatically get the right abundance today. So in the early universe, so a lot of these are their own antiparticles, and they would annihilate among one another until the universe expands so much that they don't reach each other anymore. Well, and if you calculate how many are left, and again, the only ingredient in this calculation is the annihilation cross-section. You put in a weak interaction cross-section, so then you'd get the right answer. And that's sometimes called the WIMP miracle, and perhaps it's the WIMP coincidence, but anyway, there it is. The second reason people are interested in WIMPs is because they are automatically there in supersymmetry and in other theories. So in supersymmetry, for every particle we know, there's a partner. And these supersymmetric particles are unstable to decay until you get to the very lightest one, which is stable. And that might be that would be the WIMP candidate. All right, so there's a theoretical motivation. That's good. Now, how do we go about looking for these things? Well, there's a three-pronged approach in standard with this is the same Feynman diagram, but it's kind of silly to put it 3 times, but here you read it from left to right in the 3 different possible ways of doing that. And also the 4th prong, dark stars, which is my baby, and I hope to have time to get to that. Let's start with production. So you have 2 protons colliding, and they would make the dark matter particles. And of course, we would go to CERN, to the Large Hadron Collider, to look for that. So again, you have protons traveling in opposing directions in this 17-mile ring. And then where they collide, there are detectors, and you look for what comes out of those collisions. And I have to show a few slides. And this one is a Fabiella Gianotti, who was the spokesperson on Atlas for the Higgs search and is now Director General at CERN. So the two big detectors of interest to what we're doing are Atlas, which is this one, and with this guy standing there to show how giant these detectors are. And then the other one would be the CMS detector with Peter Higgs standing in front of it. And as we all know, the first major success of the LHC was that it discovered the Higgs boson at 125 GeV. And a second major goal from the beginning, if you asked David Gross, he would have said, Susie, what is the LHC looking for? Well, supersymmetry, where you would have the proton collisions leading to a chain of supersymmetric particles, and then the lightest one, which might be the dark matter, would escape detection. Now sadly, nothing has been discovered yet. However, I wanted to comment on that. So even the minimal supersymmetric standard model has 105 parameters. And so if you want to plot something on one page, which is what's done here, you have to look at a subset of those 105 parameters. So if you unify all the fermions at a high mass, and then you unify all the bosons at a high energy, sorry, you unify them at high energies, and then you let it run down to the current energies. So for example, you unify them at a gut scale and you let them run, then that takes you down to 5 free parameters, and all of a sudden you can plot things on one plot. So if you do that in this constrained minimal supersymmetric standard model, then you get plots like this. Out of date, this was 2014, but the basic situation is the same. You have to stay above and to the right of these lines because nothing has been seen. So some people read that as that, oh, supersymmetry is in trouble, but that's actually not true, because we knew from the beginning that the LHC might not be able to detect supersymmetry. It might be at higher scale. It might be less simple than this constrained models I've been talking about. And by the way, even if you did find it, you still don't know if you found dark matter or not, because the things that left the detector only lasted fractions of a second, and we need something to last the age of the universe if it is to be the dark matter. So we have to go look in other ways for the astrophysical dark matter particles. And one way to do that is with direct detection underground experiments. So we were talking about how there are billions going through you every second. Well, let's take advantage of that and have some nucleus sitting there waiting for the WIMP to hit it. And when the WIMP comes along, then the nucleus recoils and absorbs a small amount of energy from the scattering. In fact, it's a KeV energy deposits, and the expected rate less than 1 count per kilogram per day. Incredibly tough experiments, but you're taking advantage of the fact that there are all these WIMPs in the galaxy. Which leads me to, how did I get into dark matter? So I have to always give a great thank you to my advisor, David Schramm, who was one of the founders of the field of particle astrophysics. And so advice to students, find a great mentor. He really was that. And so then when I moved on to the Harvard Center for Astrophysics as a postdoc and went to a conference in Jerusalem where I met this guy, Andrzej Drukier. He's Polish and he speaks English, French, German, and Polish all at the same time, but he had done something really interesting, which was with Leo Kodosky. They figured out that you could have the elastic scattering of neutrinos off of nuclei, and then that would be a way to look for neutrino scattering. And then Goodman and Witten said, aha, but if that's the same weakened interactions that WIMPs would have, so let's go look for WIMPs. So we invited Andre up to the Center for Astrophysics, where David Spergel, the three of us, David Spergel, Andre, and I, wrote the second paper ever on trying to look for WIMPs with these kinds of scattering processes. So I calculated Feynman diagrams and I had to learn the nuclear shell model, which I nearly flunked out of grad school because I didn't learn it in time for the quantum mechanics final. But anyway, I learned it eventually. And David looked at, well, what is the right WIMP distribution in the halo? And so we looked at a Maxwell-Boltzmann distribution. And so so here's this is a very simple equation here. This is number density times cross section times velocity. This is the interaction rate. And you can split it into two pieces. You can split it into the particle physics side over here, which depends on the exact nature of the scattering. And I will mention there's many possibilities, but the vanilla one has been independent, where the cross-section scales with the atomic mass squared, where A is the atomic mass of the nucleus that you're scattering on. But that's not the only possibility by any means. And then over here, this is the velocity, this is the astrophysics side of things. And so what we did was put in here for the velocity a Maxwell-Boltzmann distribution, where the typical particle speed is a few hundred kilometers per second. So, and then if you want to build something like this, you have to go into underground laboratories because you have to get rid of cosmic rays. So this one, for example, is Snow Lab in Canada, 2 kilometers below ground. So after we did these calculations, we convinced people, hey, start building these things. And we never in a million years thought that this would happen. So they're all over the place now, these experiments. And the only one that has a hint of detection that we don't know what to think of is the DAMA experiment in the Gran Sasso tunnel outside of Rome. And so of course I have to tell you about that. So what's going on here is what they see is an annual modulation that we predicted, which is due to the following reason. The sun is moving around the center of the galaxy, which means from our perspective, it's like a wind of WIMPs coming at us. It's like when you're driving and it looks like the rain's coming into your windshield, but it's just the fact that you're driving. So the sun has this motion around the galaxy, but then there's also the motion of the Earth around the sun that means that the relative velocity with the WIMPs changes with the time of year. And so we predict that there should be a annual modulation in the count rate with a peak in June and a minimum in December. And guess what? This DAMA experiment made of sodium iodide crystals sees exactly that. Well, might as well go to the next slide because they've got tons of data now. It goes on and on for 13 years. It's a 12 sigma result. They definitely have something modulating annually if we only knew what. Is it dark matter or isn't it? Well, it would really help if they would release their data, but they don't. And then the other thing is this peculiar is the other experiments do not see anything. They have null results. However, the other experiments are made of other material. And here's a fun comment of Juan Colliar commenting on Rita Bernabe, the leader of the DAMA experiment, and Eleanor Prelay, PI on xenon. I'm a Spaniard caught between 2 Italian women. So lots of interesting personalities in this field. So now the problem is if we want to compare DAMA positive results to other experiment negative results, it's really difficult because they're made of different material. That's why I was mentioning from the beginning that I was going to look at this cross-section depending as A squared, the vanilla spin independent cross-section. So then you can divide out the atomic mass squared and plot everything on the same plot. So here's WIMP mass on this axis, and here's the cross-section, the strength of the interaction. So if you make that assumption, then DAMA would be one of these 2 regions in green. But the experiments made of xenon, lux, and xenon tell you have to be below the red and green curve. So obviously that's not going to work. But who said it had to be spin independent? It doesn't. So that makes it the situation more confusing. And by the way, I do have to give you an update. That previous slide was really out of date. So here are the bounds from the experiments this was in 2019. I also want to mention work of Francesc Ferrers, which I think is very interesting because he removes the halo model out of this and does halo independent bounds, which are combination of this direct detection plus indirect detection I haven't talked about yet, the annihilation to neutrinos that you would see in ice cube. So here is the standard plot that people show, but if you remove the halo dependence, you still have these really powerful upper limits. So that's quite remarkable. The future situation with the future experiments, they're going to keep going down, down, down in cross-section until you run into neutrinos. You're going to find solar neutrinos, you're going to find atmospheric and supernova neutrinos, and then you have to figure out from the spectra and so on which is which. But people are doing it, they just keep going. I would be remiss if I didn't mention that xenon actually does have an excess right now, very near their energy threshold at 2 to 3 keV. Okay, so this is what was expected, and instead they have this sticking up here, and people were wondering, oh my God, is that evidence for dark matter? And I don't think it is. Actually, I'm quite sure it is not. The only thing that matches that spectrum would be axions from the sun, But if you're going to get axions from the sun, you'd also have axions coming out of other stars. And so that's just ruled out because we know about the cooling of white dwarfs and other stars, and it just doesn't work. So that excess is still sitting there unexplained. Maybe it's statistics, I don't know. But anyway, I did think I should mention that. All right, so we still have this DAMA annual modulation, and the bizarre thing is no one has an alternate explanation. It's not radon, it's not atmospheric muons, blah, blah, blah. So what the hell is going on? Well, the only way to know is build other experiments of the same material. In fact, that's when I started taking it seriously, when Frank Price at Princeton, who used to do T violation, he's very, very careful scientist, said, let's go, we have to test this. So 3 groups are also using sodium iodide crystals. Sabre is the one with Frank, and also cosine 100 and Anais, and 2 of these 3 now have data. Cosine 100 has this is the phase of the modulation, so peaking in June is what DAMA has, and so there you go. And the cosine 100, this is statistically not significant yet. So but anyway, the point is, give it 5 years and we'll know. This came out just a few weeks ago on Anais in Canfranc in Spain. This is the modulation amplitude, and this the blue blobs here, that would be the DAMA result. And these are the 1, 2, and 3 sigma results from Anais, but they have only analyzed their signal in very large bins, 1 to 6 keV or 2 to 6 keV. But the point is, they're in 3 sigma tension with DAMA, and so unless cosine comes in right in between the 2, I think we're going to have an answer, as I said, in the next few years. So it's about time that we know what's going on there. So as far as status, as I mentioned, comparing apples and oranges is hard, and so thank goodness that the sodium iodide crystals are being made by others as well. And then as far as the theory goes, there's many, other than spin independence, there's all different other types of operators people have tried. The nuclear physics also turns out to be more complicated, so we'll see what comes of that. Now, if you want to go below this quote unquote neutrino floor, you would need to, where the neutrinos become competitors for what you're looking at, you need directional capability. So what I mean by that is if you can figure out what direction the WIMP came from, well, in the direction of the WIMP wind, you'd expect 10 times as many as in the opposite direction. That really allows dark matter discovery with much lower statistics. So that would be really wonderful. So we've proposed a couple of ideas on how to do that. One of them is, yes, this is gold with DNA attached. And yes, you can buy that from Illumina Inc. with 200 bases hanging down. So this company sells them for a few $100, but not radio pure, so it's not good enough for us. But anyway, this is a nanometer thin layer of gold. And yes, it has DNA strands attached. So when the WIMP hits the gold, it knocks a gold nucleus forward into the DNA. So then these are not WIMPs breaking DNA. This is gold breaking the DNA. And you can go back and reconstruct, because you can sequence what's going on here really well, make as many copies as you like. So you could figure out this track of the gold and then conclude where the WIMP came from initially. So that's a really cool idea. We've got these wonderful geneticists. George Church actually started building this thing, but anyway, right now he's got a little pieces sitting in his freezer. We also suggested paleo detectors as another way to go, which is instead of using a ton of xenon, what if we have a very small rock, but it's been sitting underground for 1 billion years collecting tracks? So we've been trying to work out that idea. It's fun. Okay, so I talked about 2 of the ways to look for WIMPs, and the third one is indirect detection, but I don't want to spend a lot of time on this because I want to get to my other projects that I want to tell you about. But dark matter annihilates in regions where there's a lot of it through a chain of standard model particles, and in the end you get neutrinos, gamma rays, and positrons as the final end products, and there are experiments looking for each of these. So IceCube looking for neutrinos, AMS found an excess of positrons, and this is aboard the International Space Station, and they were claiming we've discovered dark matter, but that cannot be true. Again, my favorite author, Adams here, they looked at, in order to get the AMS result to be from annihilation into, I can't read this channel because Mark, your face is over the top of it. I think this might be BB bar. So then the cross section versus mass, this is where you'd have to be to explain the AMS data, but the Fermi gamma ray satellite doesn't see signals of that from dwarfs, so you have to be below the blue line. So no way does that match. And so they checked this channel by channel. So this AMS experiment cannot be from dark matter. The one that's still interesting though is the Fermi satellite. This is looking at I wish these things would stop jumping, the gamma ray sky. And in the middle of these giant bubbles, there's a very small spherical region in the middle, which is an unexplained axis that could be from dark matter annihilation, although it's the subject of a lot of controversy because it could also be pulsars. So the bottom line is we have the direct detection, the DAMA annual modulation, also I should have put in here also the xenon excess. And we have this Fermi gamma ray excess from indirect detection. So these are the things we don't know the answer of what those are. But I do want to have the time to tell you about dark stars. So this is an idea that I had together with Doug Spolyar and Paolo Gondolo. And we named them dark stars before we knew about the cult film that obviously predated us. So the idea here is that these would be stars that they would be the first stars to form in the history of the universe. We have many collaborators at this point. And the first stars to form in the history of the universe could be powered by dark matter annihilation rather than by fusion. I have to say very strongly, dark stars are made almost entirely of hydrogen and helium, okay? Dark matter constitutes only 0.1% of the mass of the star. So these are not things that are made of dark matter. They're made of hydrogen pretty much. It doesn't take much dark matter to power them. So as far as how this works, when the universe was about 200 million years old, there were proto-galactic halos of dark matter that weighed about 1 million solar masses. We call them mini halos. And the first stars start to form, you collapsing clouds of hydrogen right in the middle of these mini halos, right where there's a ton of dark matter. And as this molecular cloud collapses, it pulls in even more dark matter, just by gravity. And if these dark matter is made of WIMPs and they annihilate among themselves and produce annihilation products that mostly don't go very far. So the annihilation products include electrons, positrons, and photons that collide with the hydrogen and get trapped inside the cloud. And once they're trapped inside, they heat it up. The WIMP mass is converted to heat for this object, and actually you actually get a real star. So not only do you stop this collapsing cloud, but you get a real star. So as far as big picture goes, you have this new phase of stellar evolution that could last a long time as long as you have dark matter power. In fact, although they start out about 1 solar mass in size, they can grow really large, like 10 million times the mass of the sun, and 10 billion times as bright as the sun, which means they could be seen in the James Webb Space Telescope. I'll just sort of give you, this slide kind of gives you the big picture. You have these objects that form, then you can look for them with the upcoming James Webb Space Telescope, which is very exciting. And they also have the big plus that once they die, then they're going to collapse to black holes. And if you have million solar mass black holes at a redshift of 20 or 10 or whatever, that's really great for explaining supermassive black holes. So let me fill in a little more information now. So as I said, when they form, well, do I have a slide about what they look like? I don't, that's too bad. Anyway, so when they form, they're about 1 solar mass in size, and they're very odd. They're big and puffy. They are about 10 AU in radius, in other words, 10 times the distance between the Earth and the sun. And they're very cool. So there's absolutely no fusion going on because fusion needs heat. It needs a much higher temperature. And the dark matter is spread out uniformly. So the dark matter heating is spread out uniformly throughout this whole 10 AU thing. And because it's so cool on the outside, it can just accrete more and more mass. There's no UV photons coming out that prevent further accretion. So we let her rip. So we let them grow. So depending on the WIMP mass, this is the HR diagram of these things. So they start out small and they grow, getting bigger and bigger. And once they get big enough, well, it wants to keep jumping to the slide. Fine, we'll go to the slide. Then they become, if they're million solar mass in size or whatever, then you can see them in the James Webb Space Telescope. So Here's the predictions for the telescope, and here you see that indeed these things are bright enough to be seen. So yes, at that point, the PI John Gardner and John Mather of the JWST got very excited, and they asked us to really calculate what could you look for. So this is the kind of thing that you would look for. Okay, and what happens next? Well, these stars, if they're small, they'll get if they run out of dark matter, they'll start to collapse and they heat up. They could have a fusion phase, or if they're big enough, then they just collapse directly to black holes. And so, as I mentioned previously, briefly, if you have a 1 million solar mass black hole, well, that thing is great to explain, either be a precursor for, or if you merge a bunch of million solar mass black holes, it's a lot easier to explain the supermassive black holes, especially at high redshift. So there's already billion solar mass black holes at redshift of 6, or here's one redshift. This is a 10 billion one, solar mass one at a redshift of 6. It just goes, these are really, really early black holes, 800 million solar mass at redshift 7.5. And there's people don't know how to make them. This is a big black hole problem. And so if we give them precursors, that's helpful. Okay, so as far as dark matter detection, I've mentioned all these different ways of going after WIMPs. And dark stars, by the way, don't have to be powered by WIMPs. Other types of dark matter might work as well. And as far as, I want to give you a big picture of what is unexplained in addition to what I talked about. So I mentioned the DAMA and the Fermi WIMP hints of detection. That's all I'm going to say. And I didn't really have time to talk about these. So there's also an X-ray line, which would be consistent with 7 keV serial neutrinos. And that X-ray line is from a number of different sources. Different clusters and so on, and as well as the galactic center. So that's an interesting possibility. There's also an excess that could be due to MEV dark matter. So there's a bunch of hints out there, but as yet we don't know what's going on. So one thing I've turned to recently is, instead of looking in specific for a dark matter particle, to study the nature of dark matter using GAIA data. And this is fun because the data are there, and there's positions and velocities of 1 billion stars in the Milky Way. And if you know, and the stellar kinematics are determined by the gravitational potential of the Milky Way. So by watching stars move, you can learn about the underlying nature of dark matter. And this is kind of amazing, the progress of the resolution of these different of starting from, Hipparchus, I don't know what century that was, on till today, of this GAIA, the errors of the best stellar positions and parallaxes, look how well GAIA is doing with its billion stars. So the question here is, what is the nature of the dark matter? And the standard is always cold dark matter, but we don't know if that's right. So the lambda CDM, the C stands for cold, and it would predict from this, according to the simulations, if this is the density versus radius at the centers of galaxies and clusters, there should be cusps. Okay, so this density goes up as sort of like 1/r as you go to the center. However, in some objects people looked at, it looks like there might instead be cores, although the observations are not clear. And as far as this, so the question is cold dark matter in trouble? Well, not necessarily, because because all the simulations until recently were only with dark matter only. But if you put baryonic physics in there, like supernovae and other things like that, then the cusps could turn to cores. So maybe even with cold dark matter, you would get cores instead of cusps. But anyhow, this has motivated people, and some other of these little inconsistencies, I shouldn't say little, inconsistencies have led people to study alternatives such as self-interacting dark matter or warm dark matter. And so to learn about the nature of dark matter, we are using GAIA data. In particular, we're looking at stellar streams. So we know that the Milky Way has about 70 of these streams, okay? They're stellar streams which have dark matter associated with them. So the JLM stream, the GD1 stream. And what we're interested in is, well, how do these things form? Well, they're known to form in 2 ways. One, by dwarf galaxies. Well, so all kinds of things are merging with the Milky Way, being eaten by it. So that, for example, the Sagittarius dwarf galaxy on the other side of the galactic center, there's the 2 tidal arms, the Sagittarius stream that's coming towards us. So the tidal stripping of dwarf galaxies is one way to form them. The other one is tidal stripping of globular clusters of stars inside these subhalos. Well, for those of you who don't know, globular clusters are dense old star clusters forming at redshifts of 2 to 4. They weigh about 10 to the 5 solar masses, and they reside inside halos of galaxies. So here's the kind of scenario we're looking at. These are my collaborators, and so if this is a simulation of a Milky Way galaxy, well, this is just a picture of a Milky Way galaxy, and this subhalo is coming into the Milky Way galaxy, is going to get shredded apart. Now, inside this subhalo, you have this 10 to the 5 solar mass globular cluster that's orbiting around here, and it gets shredded apart first by the subhalo and then by the Milky Way halo, and you end up with a stream. So these are numerical simulations of this process. And the thing that's interesting is we can learn about the subhalos by looking at the streams. So the streams that we have today, if the subhalo had a cusp, you'd get quite a lot of structure in this stream. Whereas if the subhalo was cored, it's much narrower, and that's true both physically and dynamically. And so the cored ones are over here, the cuspy ones over here in the simulations. And so what we're going to do now is go and compare the simulations to the real streams. And our first comparison indicated a preference for cored subhalos, but we don't really know yet. So let's do a better job. If, for example, if that were true, then either there had to be baryonic feedback, or you must go beyond the cold dark matter scenario. There's also another way to go after information about dark matter using streams, and that's by these gaps, because something went through the stream to produce the gaps, and you can learn about the dark matter. So I don't have a whole lot of time left, but I do want to just say that there are many ways that you can test this cold dark matter hypothesis with GAIA. So I've talked about the streams being, the stream widths being different, telling you about cored versus cuspy subhalos, gaps in streams, shape of the Milky Way halo. Subhalos that pass through the Milky Way disk would have left residual observable oscillations. And there's also a lot of work going into better estimates of the local dark matter density, because that's what we need to do the direct detection experiments. And again, GAIA data is providing, well, the answer is always 0.3 GeV per cubic centimeter, but that's really good that the GAIA data is giving you that no matter what you do. So to summarize, neutrino mass is about 0.1 EV, and we're close to knowing the answer to some degree because cosmology is so powerful. WIMP searches, DAMA is an interesting situation, but it's being tested, and so we will know. Dark stars is fun. The first stars could have been dark matter powered with no fusion in there. And then I also think it's very interesting to use this stellar data from the GAIA satellite as a test of cold dark matter. So I do think I have 1 minute left to tell a joke. Okay, so I haven't said much about dark energy, and well, I don't have time to talk about everything, but also the reason is that, well, this stuff we know about. We know matter experiences gravity, so at least we know that much. So it's positively attracted. Dark energy, we might as well call it gobbledygook. We know so little about it, but the only thing we do know is that it is causing the universe to accelerate, not just expand, but accelerate. And so there's some kind of negative pressure, something repulsive going on and we don't understand it. So on the theory side, we've got a real conundrum trying to figure that out. And on the observational side, we will learn, is it time independent or time dependent? We'll get some of that information. But basically, so the only thing we do know is that it's something repulsive causing galaxies to accelerate apart from one another, which leads me to my joke. So the three of us this is at the World Science Festival in New York in 2011. The three of us were discussing, oh my God, that was 10 years ago almost. We were discussing dark matter. And these three guys were talking about dark energy. And so I just said as I said, there's only one thing we really do know about dark energy. So I made that following statement, which was a perfect place to end my colloquium. Other than I'll even end on this. This is the book Mark mentioned, The Cosmic Cocktail. So take a look if you get a chance. And now I have to decide, do I want to stop sharing while I take questions so I can see people better? I think I will. I can always open it up again if I need to.
Oh, that's fantastic, Catherine. Thank you so much. What a very interesting and entertaining talk. So, okay, at this time, let's take some questions from the audience. Audience, please enter questions into the chat. Questions? I'm looking to see if there are raised hands. And I guess maybe while people are thinking about questions, I'll mention something maybe for the benefit of the Earth and Planetary Science contingent. At one point, you showed a slide and you mentioned the homestake location and where the Davis experiment is, and gold and underground rocks. And I thought, you know, that's really very interesting. And for me, personal, because I used to live in the Black Hills of South Dakota and went into the homestake
you're kidding
mine.
me. Oh my gosh.
And went into the homestake mine to look at the gold deposits. And of course, as we know, that gold is no longer mined there, but the Davis experiment is going full blast, I guess, still, and trying to measure neutrinos. So it's pretty exciting.
Okay, so I have to say that the U.S. underground labs, I mean, that's one of the key places where these dark matter experiments are going to. So this they're no longer mining, so they're putting experiments down there. It's wonderful.
There are a few questions already. Maybe we start with a question from one of our graduate students. Meruyer is asking if you can say a few words about how does the detection of dark matter differ from the detection of dark energy?
Well, they're completely different things. So matter is gravitationally attractive, and we think it might be some kind of particle. So we're looking for that particle. Well, dark energy cannot be a particle because that would be a subset of matter. It would be gravitationally attractive. We don't really know what it is. The standard thing that people talk about, and again, is lambda CDM. The lambda there is a cosmological constant, which is a vacuum energy. And the vacuum energy is a real thing. So in this room, in your room, everywhere, there are particle-antiparticle pairs that pop into existence and then go away again. And they last 10 to the minus 43 seconds or something like that. But this actually really happens. And if you add up all of that, then it gives you, then it produces a vacuum energy. And in fact, it's been measured. So what it's called the Casimir effect. People have looked at two parallel conducting plates, and because of the vacuum in between, they're attracted to one another, and that's been measured. So vacuum is a real thing. And it doesn't mean vacuum in the sense of having nothing in it, which is the colloquial sense of the word, but it's a real thing. But you know, that's something completely different from particles, which is what we think the dark matter is made of. But the way that we're studying dark energy, like trying to understand, I mentioned, is it time dependent or not? You look at its effect on the expansion of the universe. So the acceleration of the universe and going back in time and figuring out exactly when it kicked in and exactly how that happened. That's what we're doing to learn about the nature of dark energy. The effect on cosmological expansion is the tool that we have.
That's very, very good. And then Mike Novak is asking, what do you think about the tension in the H0 measurements between early and late universe?
Oh yeah, this is
real.
This is a really interesting question. Okay, so let me explain what the Hubble tension is. So first of all, the H0 is the expansion rate of the universe today. And there are multiple ways of trying to figure out what the value is. So one way is to go back exactly these cosmic microwave background peaks that I talked about, that I showed that picture of the Doppler peak at 1 degree and da 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 da. So if you analyze the cosmic microwave background, you get a measurement for the Hubble constant, which is 67 kilometers per second per megaparsec. However, if you look at the late time behavior in the universe with the supernovae, which is how we learn about dark energy, and this is much, much later, what the supernova are doing, then you get a value of H0, which is 72. So it may sound like 67, 72 is not a big deal, but guess what? It's actually a 5 sigma discrepancy. And so people are taking it seriously. And I kept thinking, you know, when I was in grad school, some people insisted it's 500, others insisted it's sorry, 50, others said it's 100. Well, now we're at 67, 72. Come on, we'll get over it. But what I think is really cool is there's an idea called early dark energy, originally coming from Mark Kamiankowski, where if there is just before the production of this early light, in other words, right at the epoch of matter radiation quality, for those of you who know what it means, right before the cosmic microwave background is produced. If there's a brief period also of vacuum domination, then it'll change the result you get out of the CMB for H naught. It'll raise it a little bit because it speeds up the expansion by having more stuff there, and so therefore the length scales are shorter, and it all works out so that you end up with values of H naught that agree. And so when I heard Mark's talk, I thought, oh my God, that looks like a phase transition to me. You have a vacuum energy, and then suddenly it shuts off right at this point. And so I've written a paper now called Chain Early Dark Energy, where we have a series of phase transitions. And this early dark energy, this additional vacuum, only has to be 10% of the total energy at that point, and yet it's enough to explain the discrepancies. So I thought, wow, that's really fun. Now, is it going to turn out to be systematics of one of these experiments or another? I don't know. But in the meantime, as theorists, we got to go for it, you know, so I'm going for it, trying to explain it.
Actually, people can unmute themselves and speak. Jim Bagley had a question.
You didn't expect that long an answer.
No, it's very good.
It's my favorite subject right now.
No, but maybe Jim, do you want to ask your question, because I'm talking and I think.
Okay, I guess my question, having worked as an experimentalist on a bunch of different things.
Oh, I see Shmuel knows enough. I see Shmuel.
Yes.
Hi, how are you?
Inventor of asymmetric dark matter that I didn't have a chance to talk about, but just so you all know, he thought of it decades before anybody else. Anyway.
Which is in my question, by the way. So I said, what would you, if you had to really bet real money, like if you really had to bet your life on it, I mean, I guess what would be you bet on, or what would be your ranking? And I had WIMPs, axions, or asymmetric dark matter, because Shmuel is a really smart guy.
You know, I refuse, but I did do a bet with Frank Wilczek, but that was an easy one because I bet that I bet on WIMPs in DAMA, because if I win, if I'm right, I get $1,000. But if they're ruled out, are they going to be ruled out in a certain time frame or not? He only gets one. So I thought, yeah, of course, I'll take that bet. Take 1,000 of those bets.
And Wilczek wants axions, right?
Yes, he invented axions, so he wants axions. Yes. So I still think that WIMPs and axions have the best motivation. Nowadays, people are considering a wide range of possibilities. I suppose I should have showed that slide all the way down to 10 to the minus 22 EV. In which case the de Broglie wavelength would be longer than the size of the galaxies. So that would be useless. And all the way up to, I don't know, 10 to the plus whatever, not quite the Planck scale, but going after stuff just because it hasn't been ruled out yet is not the same as going after stuff that has a motivation. So I'm still happier with the ones, you know, the ones you mentioned.
And just as a follow-up, I mean, people are ready to abandon WIMPs, the WIMP miracle WIMPs, the thermal WIMPs, which really annoys me because, you know, the whole motivation for it was this beautiful story of the WIMP miracle. And now if you're looking in other little corners of parameter space, you know, would you have ever proposed it in the first place? I don't know.
Well, while we're on that, the calculations that we did, which, you know, gave people event rates and detectors, well, that's pretty fortuitous. The things that we picked gave pretty high event rates compared to what people are going after now. But if we happen to look in the wrong regime of parameter space, nobody would have ever built anything. Right? That's funny.
Hey, other questions?
I actually had one. Can you say a bit more? I was very interested about this thing you mentioned about the pair instability of massive stars and how you can address that by adding another. So basically, you can make more massive black holes, no?
Yes. Well, actually there was a it's called the black hole mass gap. There's a specific window that wasn't going to work. The ones that were going to blow up. So either heavier or lighter was okay. It was just there was a window that was supposed to be ruled out, but they found them in that window. And so we just said, okay, I've been doing stellar physics anyhow because of dark stars, right? So we already know how to run the horrendously giant MESA stellar evolution code. And so a student put in an arbitrary heat source, and the question is, can you quench this pair instability explosion? And you can. So if
So
you want to
basically, you're
ask,
adding an extra energy source.
we're adding an extra energy source. Yeah.
I see. I see. Very good.
Yeah, and I don't care what it is. Well, I do care what it is, but I mean, we were agnostic as to what it is.
So. But it could be like WIMPs that are trapped in the center, or
Absolutely, yes, it could.
Very cool.
Mm. Now, what he's looking at now, he did 180 solar mass stars. So now he's looking at, the question is, did we move the mass gap or did we eliminate it completely? So we have to look not just at one particular mass, but we have to look at a range of masses. And he only did 100 GeV WIMPs, and so no, wait, what am I saying? He didn't do WIMPs. What am I talking about? Sorry, I'm mixing up dark stars in this project. But he does have to do other mass stars.
Well, Katherine, I have a question, and I'm not a physicist, and I've learned an awful lot today, but I still don't know very much. And one of the question that I have is, what are some of the other things that we might learn, for example, about black holes that would help us understand better or test some of these ideas? For instance, how well do we really understand the energy state and what's going on around black holes in terms of their the gravity, magnetism, and so forth? And we know there are massive black holes at the center of galaxies, but how many are there in the universe, and so forth? Are there things that we can better understand, for example, about the way black holes work that will help us with dark matter and dark energy searches?
Oh, specifically for the dark matter, dark energy searches you're talking about. Because I was going to say black holes are a huge subject, both on the theory side. There's it's a big part of string theory. Big thing in string theory is to understand the information loss paradox. So on the theory side, there's an enormous amount going on. And on the experimental side, there's all these different possibilities. So the supermassive ones have nothing to do with dark matter. There's not that much mass in them. So like the one in our center of our galaxy, 4 million solar masses, but our galaxies 10 to the 12 solar masses, so supermassive black holes are irrelevant to the dark matter problem. However, since this new result just came out yesterday, I am going to say something about it. They found, so the Event Horizon Telescope was the one they produced these bright regions, looks like donuts, that are supposed to show you, here's the black part in the middle is the black hole. So now they've gotten polarization of that light, which is, I don't know how they're able to do that. That's pretty interesting. And so they're learning about magnetic fields, which play a major role in producing the jets coming off of the supermassive black holes. So there's a lot of interesting physics being discovered there, but that has nothing to do with dark matter. So if you want to do, however, it is also weird to think between us and the center of the galaxy, there could be millions of black holes of a variety of different masses, and we just don't know about them, And so they could be a major contribution to the dark matter. Now, so for example, if they're left over from dark stars, they would have dark matter around them, okay? And the dark matter, you could look for the dark matter annihilation that's on their surfaces, from the dark matter that's still on their surfaces. So it doesn't even have to be from dark stars, but black holes that have collected dark matter around them would give annihilation signals you can look for. So that's one thing you could look for. But primordial black holes is a hugely popular topic right now, I'll tell you. So and the other question is the gravitational waves. Can you get a stochastic signal? So we wrote a paper with Lisa. If you have a bunch of primordial black holes falling into the supermassive black holes at the centers of galaxies, you'd expect a stochastic gravity wave signal. Who is doing gravity waves from black holes? Is that Francesca? Are you doing that too?
Yeah, and Bupal, my colleague Bupal. But we did we did gravitational waves from phase transitions.
Basically. I see. Yeah. Oh yeah, I did some stuff on that too. Yeah. That's right. Okay. That's how I knew. I was thinking, wait a minute, I've seen your work on this. That's why. Okay.
With
Tom Giblin, right?
No, that was and my other colleague, Jim Mertens, who is here,
Oh,
has done
okay. So I'm mixing.
si-
I see.
yeah. So he's done simulations on
Of the
yeah.
gravitational waves.
Not really. I think, well,
No?
maybe he can explain it better. More of the, as far as I know, of the cosmological evolution and GR effects on that. Well, it's related to, but yeah.
I might be interested because of this early dark energy stuff I've been
Yep,
talking about.
that might
So
be a very,
we should
yeah.
talk actually.
Yeah, we can talk after.
I should talk with both of you. I should talk with both of you independently of this colloquium.
Yeah. Maybe after, like now when we say, there is one maybe last question, Henrik, you want to ask it or?
Just wondering if these ssDNA detectors sound like pretty exotic, if that is feasible and how long you can keep DNA to work there, you know.
Well, so the biology, so first of all, the attaching DNA to stuff, as I said, that's easy. They're already doing it. So that part's easy. Keeping the DNA straight is not easy. So that's why George put it in a centrifuge. So you can straighten them out, keep them straight, because they don't feel gravity at all, you know, they're too light. And then, so once they break and they fall down, if you can figure out how to capture them, then you can make 1 billion copies easily and sequence it easily. So the irony is the biology side is easy. That's what was stunning to me, that this was again with Andre Drukier. We went over to his pal's house, George Cantor, and it's in San Diego, you pass the Maserati on the way to the swimming pool. And we're talking, these are, you know, academic biologists who I guess they started companies or whatever, but anyway, and they're all saying, yeah, that's easy. And I was like, oh my God. But the hard part is having this, like this gold has to be radioactively really pure. The DNA has to be radioactively pure. So it's the background signals, I think, that are frightening people when you have a surface like that.
Right, thanks.
So it's the physics that's hard, not the biology.
Mm-hmm.
Okay, I don't see any more questions in the chat. And so I think the Q&A is sort of coming to a natural end, and unfortunately we have to end it here. I'd like to once again thank Professor Freese for a wonderful, stimulating, and very, very entertaining lecture on what certainly is one of the great outstanding scientific questions of our time. As a small token of our appreciation for this great lecture in advance of the public lecture, which begins tomorrow night at 7 p.m. Central, and you're all invited, by the way, we have a gift that we will send to Professor Freese. And if you will indulge me for just a moment, I will attempt to share my screen and show you this. Can you see this okay?
I have to hold on a second.
You should be able to see it.
Oh, I love it.
So you see the shape of the arch, which
I do. I get it. Yeah, that's so cool.
And this is glass, and to give you a sense of scale, it's about 22 centimeters tall, and it's engraved with Professor Freese's name and the McDonald Distinguished Lecturer, March 24 to 25, 2021. So again, we are so very, very appreciative of this wonderful lecture, and I look forward to hearing about this again at the public lecture tomorrow evening. So at this time,
Brad, you are too kind. I love it. It's really nice. Thank you.
Well, fantastic. We're very pleased. So at this time, what I'd like to do is invite those who might want to hang on for another 20, 30 minutes to speak informally with Professor Freese to do so. And for the rest of you, bid you a good day, and thank you very much for tuning in. Again, I hope everybody has enjoyed this lecture as much as I have. Thank you so much.